Welcome to this coding problem walkthrough. In this session, we'll tackle LeetCode problem number 1573, titled Number of Ways to Split a String. We'll explore various approaches, beginning with a brute force method and progressing to more efficient solutions. Let's get started. In this problem, you're given a binary string S, which is a sequence consisting only of zeros and ones. The goal is to determine how many ways you can split this string into exactly 3 non-empty parts such that each part contains the same number of ones. Since the number of possible splits can be large, the result needs to be returned modulo 10 to the power of 9 plus 7. Let's look at the structure of the input and output. The input is a single binary string S of length n, where n can be as large as 100,000. The output is an integer representing the number of valid ways to split the string according to the given conditions, modulo 10 to the power of 9 plus 7. Now let's explore some concrete examples to better understand the problem requirements. For example, consider the input string S equals 10101. Here, the output is 4. Why? Because there are exactly 4 ways to split this string into 3 parts, where each part contains 1. These splits are 10101, 10101, 10101, and 10101. Notice that in all these cases, each part has exactly 1, fulfilling the condition. This example highlights the importance of ensuring that each part is non-empty and contains the required number of ones. Now, let's look at another example to see how the output can be different based on the composition of the string. Now take the input string S equals 1001. In this case, the output is 0. The reason is that there's no possible way to divide this string into 3 non-empty parts where each part contains the same number of ones. The string has only 2 ones, which makes it impossible to create 3 parts, as each part must contain at least 1. This example highlights an important limitation: if the total number of ones in the string is less than 3, it's impossible to satisfy the conditions, and the result will always be 0. But what happens when the string contains no ones at all? Let's explore that scenario next. Consider the input S equals 0000. Here, the output is 3. Why? Because the string contains no ones, and in this special case, we can split the string in any way as long as the parts are non-empty. The 3 possible valid splits are 0000, 0000, and 2000. This edge case demonstrates that when there are no ones in the string, the problem reduces to counting the ways to split the zeros into 3 non-empty groups. Finally, keep in mind the constraints: the length of the string can go up to 100,000, so the solution must be efficient. Edge cases such as strings with no ones, very few ones, or very large strings must all be handled correctly within the given time limits. When approaching this problem, we can consider 2 main strategies. The first is a brute force approach, which involves enumerating all possible ways to split the string into 3 parts and checking if each part contains the same number of ones. This would require nested loops to test all valid splits, and for every split, we would count the ones in each segment to verify the condition. While straightforward, this approach is extremely inefficient, with a time complexity of O(n) cubed, due to repeated substring operations and nested iteration. Additionally, it doesn't leverage any structural insights about the problem, making it impractical for larger strings. On the other hand, we have an optimized approach that relies on mathematical counting. Here, we start with 2 critical observations. First, the total number of ones in the string, referred to as total_ones, must be divisible by 3 for any valid split. If this condition isn't met, there are no valid splits, and we can return 0 immediately. Second, if the string contains no ones at all, the problem reduces to finding how many ways we can choose 2 split points in the remaining positions, which can be calculated using a simple combinatorial formula. For cases where total_ones is greater than 0, we focus on dividing the string into 3 segments such that each segment contains exactly 1/3 of the ones. This can be achieved efficiently using techniques like 2 pointers or a single pass through the string to identify valid split points. To implement the optimized approach, we start by counting total_ones in the string. If this count isn't divisible by 3, we know it's impossible to split the string into 3 equal parts, so we return 0. Next, we determine the positions where splits are valid. This can be done via direct traversal or by leveraging prefix sums to quickly identify segments that contain the required number of ones. Once we know the positions where each segment can begin and end, we use combinatorics to calculate the total number of valid combinations. This approach ensures that the solution is efficient, with a time complexity of O(n). We only traverse the string a constant number of times, and no additional data structures are needed, resulting in O(1) space complexity. Compared to brute force, this method is not only significantly faster but also leverages the mathematical properties of the problem to simplify the solution. While other techniques, such as sliding windows or prefix sums, might seem applicable, they either fail to suit the dynamic nature of the problem or add unnecessary complexity without a proportional gain in performance. The chosen strategy for this problem is the optimized approach based on mathematical counting. This method stands out for its simplicity and efficiency, as it directly addresses the core insight, the divisibility of total ones by 3. By focusing on this key property, we can quickly determine whether a solution exists and, if so, identify valid splits efficiently. The use of direct traversal eliminates the need for additional data structures, ensuring constant space usage while maintaining linear runtime. Brute force was discarded due to its prohibitive computational cost, and while techniques like prefix sums were considered, their added complexity was unnecessary given the problem's structure. By grounding the solution in mathematical reasoning, we achieve a clean, scalable, and highly performant approach that handles even the largest inputs with ease. This balance of clarity and efficiency is what makes the chosen strategy ideal for solving the problem. In this problem, we are working with a binary string, which is made up of only zeros and ones. The goal is to split the string into 3 contiguous substrings, ensuring that each substring contains the same number of ones. To solve this, we start by counting the total number of ones in the string, which we'll call total_ones. This step is critical because if the total number of ones is not divisible by 3, it's impossible to evenly distribute them across 3 partitions, meaning no valid splits exist, and the result is simply 0. Next, we calculate how many ones each partition should contain, which is given by ones_per_partition equals total_ones/3. If total_ones is 0, the string contains only zeros. In this special case, the number of splits is determined by the formula n1 n2/2, which calculates the combinations of 2 split points within the string. This ensures we handle edge cases properly before moving forward. Now that we know how many ones each partition should contain, we move on to identifying valid partitions. As we traverse the string, we maintain a count of ones encountered so far, called current_ones. When current_ones reaches ones_per_partition, it marks the end of the first partition. Similarly, when current_ones reaches 2*ones_per_partition, it marks the end of the second partition. These positions are crucial because they define where the string can potentially be split. After identifying these positions, the next step is to count the number of valid ways to place the splits. Specifically, we count how many ways we can split the string between the first and second partitions, as well as between the second and third partitions. The total number of valid splits is then the product of these two counts. This approach ensures that each split satisfies the requirement of equal ones in all 3 substrings. There are a few key insights that simplify this problem. First, the divisibility check for total_ones is a quick way to eliminate cases where no valid solution exists, allowing us to avoid unnecessary calculations. Second, edge cases like strings with no ones or strings too short to allow 3 partitions must be handled explicitly to ensure correctness. Another important insight is the use of prefix sums, which involve maintaining a cumulative count of ones as we traverse the string. This approach is much more efficient than trying all possible splits via brute force, as it reduces the problem to a few simple calculations. By leveraging these insights, we can solve the problem in a way that is both efficient and easy to implement. To implement this algorithm, we use a few key data structures and techniques. First, a single counter, current_ones, is used to track the cumulative count of ones as we traverse the string. This avoids the need to repeatedly iterate over substrings to count ones, saving time. Additionally, we use arrays or lists to store the indices where valid partitions can occur. These indices are then used to calculate the number of valid splits between partitions. In terms of efficiency, the algorithm has a time complexity of O(n), because we only make two passes through the string, one to count ones and another to identify valid split positions. The space complexity is O(1), because we only use a few counters and variables, regardless of the size of the input. Together, these optimizations make the algorithm both fast and memory efficient. In this implementation, we start by defining a class called solution and a method inside it named numberWays, which takes a string s as input. The first thing we do is define a constant mod, which is set to 10 to the power of 9 plus 7, to ensure our results stay within the bounds of large integer operations. Next, we count the total number of ones in the string using the count method. This count is crucial because it determines how we can split the string. If the total number of ones is not divisible by 3, it means we cannot split the string into 3 equal parts containing the same number of ones, so we immediately return 0. Then, we handle the special case where there are no ones in the string. In this situation, the task reduces to counting the number of ways to split the zeros into 3 parts, which can be calculated using a formula involving combinations. Specifically, we find the number of ways to choose 2 split points in a sequence of zeros, and we return this value modulo mod. After handling this edge case, we calculate the number of ones each part should contain by dividing the total _ones by 3. We then initialize two variables, first _split and second _split, to 0, which will keep track of valid splits for the first and second parts of the string respectively. Additionally, we define a ones _count variable to count the cumulative number of ones as we traverse the string. At this stage, we start iterating over the string character by character. Every time we encounter a 1, we increment the ones _count. Once the ones _count matches the target number of ones for the first part, we increment the first _split counter, as it indicates a valid split point has been found. If the ones _count reaches twice the target number, meaning we are at the boundary of the second part, we increment the second _split counter to track valid splits for the second section. By counting these valid split points for both the first and second parts, we can calculate the total number of ways to split the string into 3 equal parts. Finally, the result is obtained by multiplying the counts of first _split and second _split, giving us the total combinations of valid splits for the string. Since the result could be a very large number, we return it modulo mod to ensure it fits within the constraints. This completes the implementation, and the method now efficiently calculates the number of ways to split the string into 3 equal parts based on the number of ones. Here, we begin our Java implementation with the solution class and the numberWays method. The first thing we do is define a constant mod with a value of 1,000,007 to handle large results and prevent overflow when performing modular arithmetic. Next, we initialize a variable total ones to count the total number of ones in the input string s. This is done using a simple loop that iterates through each character of the string. If the current character is 1, we increment the total ones counter. Once we have the total count of ones, we check if it's divisible by 3, because the string can only be split into 3 equal parts if the total number of ones is divisible by 3. If it's not divisible, we immediately return 0, as no valid splits are possible. Additionally, we handle the edge case where there are no ones in the string. In this scenario, we calculate the number of ways to split the string based on the zeros. This involves using a formula to calculate combinations of splitting the string into 3 parts and taking the result modulo mod. Finally, we calculate how many ones each part should contain by dividing total ones by 3, and we initialize two variables, first split and second split, to 0. These will help us track the number of valid splits later in the code. Now, we introduce the variable ones count to keep track of how many ones we've encountered while traversing the string. As we iterate through the characters of the string, we increment ones count each time we encounter a 1. This helps us determine when we've reached a point where a valid split can occur. When ones count equals ones per part, we know that we've encountered the first valid split, so we increment first split. Similarly, when ones count equals 2 * ones per part, we've found the second valid split, and we increment second split. These two counts represent the number of ways the string can be split after the first and second segments, respectively. Finally, the total number of valid ways to split the string is given by the product of first split and second split. We calculate this product, take it modulo mod to handle large numbers, and return the result. This ensures we account for all possible valid splits while adhering to the constraints of the problem. To solve this problem, we need to determine how many ways we can split a binary string into 3 non-empty substrings, each containing the same number of ones. The result should be returned modulo 10 to the power of 9 plus 7. For example, consider the input string 10,101. First, we count the total number of ones in the string, which is 3. Since 3 is divisible by 3, it's possible to split the string into 3 parts, where each part contains exactly 1 one. Next, we initialize some variables, first underscore split and second underscore split, both set to 0, to track valid split points, and ones underscore count, set to 0, to count ones as we iterate through the string. As we go through the string, we increment ones underscore count whenever we encounter a 1. When ones underscore count equals the target count for a part, ones underscore per underscore part, we increment first underscore split or second underscore split based on the current state. For example, at index 0, we encounter the first one and increment ones underscore count to 1, matching ones underscore per underscore part. This makes index 0 a valid split point for the first part, so we increment first underscore split to 1. At index 1, we see a 0, but since ones underscore count hasn't changed, we increment first underscore split again to 2. We repeat this process for the rest of the string, tracking valid splits for the second part as well. At index 4, we encounter another one, bringing ones underscore count to 3, which completes the third part. Now, to calculate the result, we multiply the number of valid split points after the first part, first underscore split, by the number of valid split points after the second part, second underscore split. Using our example, first underscore split is 2 and second underscore split is 1, so the result is 2 multiplied by 1, modulo 10 to the power of 9 plus 7. This gives us an output of 2. For another example, consider the input string 0000, which contains no ones. In this case, we calculate the number of ways to split the string based solely on the zeros. The length of the string is 4, so the number of ways to place 2 split points between the zeros is determined using the combinations formula. Choose 2 positions out of 3 possible gaps, which equals 3. The result is 3 modulo 10 to the power of 9 plus 7, which is simply 3. Now let's analyze the input string 111,111. Here, the total number of ones is 6. Since 6 is divisible by 3, we can split the string into 3 parts, each containing 2 ones. We initialize the same variables, first underscore split, second underscore split, and ones underscore count, all set to 0. As we iterate through the string, we count the ones. After encountering the first 2 ones, ones underscore count equals ones underscore per underscore part, so we identify the first valid split point and increment first underscore split to 1. After encountering the next 2 ones, ones underscore count equals 2 times ones underscore per underscore part, marking the second valid split point, so we increment second underscore split to 1. Finally, the last 2 ones bring ones underscore count to 6, completing the third part. The result is calculated as first underscore split multiplied by second underscore split, modulo 10 to the power of 9 plus 7. In this case, both first underscore split and second underscore split are 1, so the result is 1. Thus, the output for this example is 1. To summarize, there are a few key points to keep in mind. First, if the total number of ones in the string is not divisible by 3, it's impossible to create 3 equal parts, so the result is 0. Second, if the string contains no ones, the number of splits is determined by the combinations formula based on the string's length. Third, we use modular arithmetic throughout the calculations to ensure that results remain within the bounds of 10 to the power of 9 plus 7. Finally, the algorithm is efficient, with a time complexity of O(n), where n is the length of the string. This ensures that the solution is scalable even for large inputs. To understand the time complexity of this solution, let's break it down step by step. First, we count the number of ones in the string using the count method. This operation scans through the entire string once, making it O(n), where n is the length of the string. Next, we check if the total number of ones is divisible by 3 using the modulus operator. Since this is a simple arithmetic operation, it runs in constant time, O(1). Finally, if there are no ones in the string, we calculate the number of ways to split it using a straightforward formula. This involves basic arithmetic and also runs in O(1). These are the foundational steps contributing to the overall time complexity. Now, let's look at the part of the algorithm where we traverse the string to count valid splits. Here, we loop through each character in the string and perform constant time operations, such as checking the current character, updating counters, and comparing the count of ones to the target values. Since the loop processes each character exactly once, this traversal adds O(n) to the time complexity. When we combine all the components O(n) for counting ones, O(1) for divisibility and no ones checks, and O(n) for the traversal, the total time complexity simplifies to O(n). This efficiency ensures the solution scales well with input size. Looking at the space complexity, we see that the algorithm is highly efficient in its memory usage. The input string S is already given, so no additional space is required to store it. The solution uses a constant number of auxiliary variables such as mod, total_ones, and ones_count to store intermediate values. Since the number of these variables does not grow with the size of the input, they occupy only O(1) space. Additionally, the algorithm does not rely on any extra data structures like arrays or hash maps. As a result, the overall space complexity is O(1), making this approach not only time efficient but also memory efficient. When analyzing the best, average, and worst cases, the time complexity remains O(n) in all scenarios. This is because the algorithm always performs a full traversal of the string to count occurrences and determine valid splits, regardless of input characteristics. There is no early termination or conditional branching that would affect the runtime. Comparing this to a brute force approach, which would involve iterating over all possible split points and checking each split for validity, the naive solution could have a time complexity of O(n², or even O(n³), depending on implementation. This makes the brute force method infeasible for large strings, highlighting the necessity of the optimized approach. The optimized solution we've implemented reduces the time complexity to O(n) by leveraging mathematical insights and a single traversal to identify valid splits. Unlike the brute force method, which performs redundant calculations, this approach focuses on efficiency, processing the string in linear time. The mathematical proof for this big O analysis is straightforward: the traversal of the string contributes O(n), while all other operations, such as counting ones and checking conditions, are constant time, O(1). Together, this results in an overall time complexity of O(n). Additionally, the algorithm uses no extra data structures, keeping space complexity at O(1). In summary, this optimized solution is a significant improvement over the naive approach, offering both time and space efficiency for large input sizes. Common mistakes in this problem often stem from overlooking key details in the requirements or failing to optimize the solution. For instance, one frequent error is ignoring edge cases, such as strings where the total number of ones isn't divisible by 3. These cases make it impossible to divide the string into 3 equal parts, and failing to handle them explicitly can lead to incorrect results or runtime errors. Another mistake is relying on brute force logic to enumerate all possible partitions without verifying their validity. This approach is not only inefficient but also impractical for larger inputs. Similarly, not optimizing for time complexity can result in time limit exceeded errors, especially if you're using an O(n³ solution when more efficient algorithms, like prefix sums or sliding windows, are available. Misinterpreting the problem statement is another pitfall. It's crucial to remember that each part of the string must have the same number of ones, not necessarily be of equal length. Lastly, off-by-one errors during indexing can be particularly problematic, often causing boundary condition issues or invalid partitions. These mistakes are preventable with careful attention to both the problem constraints and the implementation details. To excel in interviews, it's important to focus on key insights that simplify the problem. Start by using prefix sums, which allow you to quickly compute the number of ones in any substring without having to repeatedly sum over the same range. This greatly improves efficiency. Another critical insight is recognizing that if the total number of ones in the string, or total ones, isn't divisible by 3, then it's impossible to make a valid split. Identifying this upfront saves significant computation time. Sliding window techniques are also highly effective, as they enable you to count substrings with specific properties in O(n) time. Additionally, for problems involving equal distribution or splitting, tools like modular arithmetic or hash maps can be incredibly powerful for optimization. Finally, it's worth noting that similar logic applies to related problems, such as LeetCode 1239, 560, 930, and 1248. These problems also involve counting specific patterns or distributions, so practicing them can help you recognize patterns and refine your approach to this type of challenge. There are several alternative approaches to solving this problem, each with its own trade-offs. The first is prefix sum optimization, where you build a prefix sum array to track cumulative counts of ones. This enables you to determine valid partitions in O(n) time, though it does require additional memory to store the prefix sum array. Another option is the sliding window technique, which uses 2 pointers to dynamically adjust the window size and count valid partitions. While this approach is efficient, it may require careful handling of overlapping windows to avoid errors. A third method involves using a hash map to track occurrences of cumulative counts. This makes range queries efficient but comes with slightly higher space usage due to the hash map. Lastly, for more constrained variations of the problem, dynamic programming can sometimes be applied to count the number of ways to split the string. However, this approach tends to increase the complexity of implementation and debugging, so it's less common. Each of these methods provides a unique perspective on tackling the problem, so understanding their trade-offs is key to selecting the right one for a given scenario. Great job on completing this problem walkthrough. To recap, we solved number of ways to split a string using an efficient approach that leverages prefix sums and mathematical reasoning. This problem highlights the importance of optimization in string manipulation tasks. Thank you for joining, and be sure to practice similar problems to sharpen your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!